And now for something completely different.
Not that different.
Okay, not that different. That's even better.
Oh, I don't think, maybe not.
So our next talk, I'm really happy that Robert Robere could come and give a talk here in spite of having teaching at an inconvenient time at McGill. And Robert has done a lot of very interesting work, both in proof complexity and computational complexity and communication complexity. And I don't even know. In particular, some of the best results on lifting theorems and use of those communication complexity techniques in proof complexity and beyond Robert's work. And hopefully you will tell us more about this beautiful set of tools that you helped develop over the last few years.
Cool. All right. Thanks for the organizers for inviting me. I'm excited to give this talk. I only have a short amount of time, so I unfortunately have to give the same preamble that Joanna did. I can't go too into details with things, but so today is just going to be kind of a gentle introduction for people into these lifting theorems for people who may not be too familiar with the techniques, and I'm sure that Susanna will talk a little bit more about these things too afterwards. Okay, cool. So, so the main message of this talk is that one of the most powerful tools that we have in proof complexity is composition. And so what do I mean by composition here? Well, if we let F throughout, we're just going to let capital F be in some unsatisfiable CNF formula. Usually we think of these clauses as being bounded width, but that's not especially important. And if we think of associated with F, say, we could have some sort of function, G, which we'll refer to as a gadget function. Just think of it as some arbitrary Boolean function. If you want something concrete for now, you can think of, say, the 2-bit XOR, but in general, you could pick something else. Then we can define a composed formula that you get from composing together F and G. So by this, I just mean take all the variables of F and plug in copies of this gadget G on fresh, conjure up new copies of variables for each of these zi's right here. Okay, and then what we'll do is we'll plug G in on these new variables for each of these z's, and then we'll rewrite this as a CNF formula. So it'll still be unsatisfiable after we do this composition. Okay. So now the kind of one of the the message of these lifting theorems that I'm going to be talking about today is basically the following. If we have two proof systems, P and Q, you could even pick P equal to Q if you like. Can we somehow relate the best P refutations of F to the best Q refutations of the composed function, of the composed formula F and G? Okay. And the surprising answer is that this is a very general question, and it's so general that it might be approaching vagueness. But the surprising answer to this question is that sometimes you can actually really say yes. And so these general family of resultant proof complexity are typically called lifting theorems. And so where does this name lifting theorem come from? Well, it just comes from the fact that if you think of P as being like a simple proof system, and you think of Q as being some sort of complicated proof system, then such a result allows you to lift analyses from P to Q, as long as you're happy with the results in Q being for these composed formulas. And the rough intuition for these things is that if this gadget G is somehow hard to compute in the stronger proof system Q, then the best thing that Q can do is just simulate P proofs for F while paying some local overhead every time it needs to use the gadget G. And this local overhead can really cause different complexity parameters to blow up over the courses of the proofs. And kind of the remarkable thing is that if we vary P and Q and G, then we can get quite strong control over a big family of proof complexity parameters. Okay, so this is kind of the general blow up, so or the general idea. So today I'm going to give everybody sort of a gentle introduction. I'm going to focus on just two proof systems, resolution and cutting planes, but there's also results known for other proof systems. So let's just start off with some concrete examples. So we can choose the inner gadget G to be XOR to start off. So let's let F just be some unsatisfiable CNF formula. Let's let XOR be the usual 2-bit XOR. Okay. And then how do we define this composed formula just really explicitly so that we have something concrete to work from? Well, we just kind of do it in the most natural way. So what we're going to do is we're going to encode each XOR as a tiny CNF itself. So every time I have a variable Zi, I'll replace it with a tiny CNF formula that encodes Xi parity Yi. And if I have the negation of Zi, well, then I can replace it with a CNF formula which replaces the negation, or like, this is equivalently the equality between Xi and Yi. And then after we do this substitution into the CNF formula F, we'll just use the distributive rule to rewrite the CNF, to rewrite the new substituted formula into CNF itself. And this is pretty obvious, but because we haven't changed anything about the semantics of F, the resulting formula after doing the substitution is still going to be unsatisfiable. So for an example, if this is our simple little CNF formula here, well, for Z1, we would substitute in the XOR of X1 and Y1. For Z2, we would substitute in the negation of the XOR of X2 and Y2, which we also encode as CNF. And then after we do this substitution, we end up getting something that looks like this. So up here, we have the substitution for Z1, and then down here, we have the substitution for this clause. And then by distributing over this red OR here, we would obtain a CNF formula, okay? And when you do this in general, it's not too hard to convince yourself that if the formula you started with had width W and M clauses, then after doing this composition, well, the new formula is going to have width at most 2W because every variable gets replaced with 2. But the number of clauses is going to blow up exponentially in the width. And that just comes from this distributive law right here. So I have 2 clauses here. If I had width W, when I do the distribution over all of them, I'm going to end up getting an exponential blow up. So in general, when we compose with XOR, it's only really sensible if you start with a bounded width formula. So even though XOR is a simple gadget, in some sense, there's many simple proof systems that people are interested in for which can't count mod 2, right? And resolution is kind of the canonical example of this. So composing with XOR already gives very simple family of lifting results. So kind of the canonical one that I think of is the following, which is just an easy corollary of a Podlekin and Polygazo. If I take any unsatisfiable CNF formula at all, then the minimal size of a tree-like resolution refutation of F composed with XOR is at least 2 to the depth of the resolution complexity, or the depth complexity and resolution of refuting F. And this kind of encapsulates a lot of the things that we see in these lifting theorems. So we have 2 different parameters, depth and size, in 2 different proof systems. In this case, they're closely related, but they're different proof systems, right? And the complexity parameter of the first guy in one proof system gets lifted to a different complexity parameter of the composed function in the second proof system. And later, if we have resolution depth in this case, so this is a win for us because resolution depth is very, very easy to lower bound. It's just the same as lower bounding like decision tree depth, which we know how to lower bound. So if you want to prove size lower bounds for tree-like resolution, well, then this gives you a totally mechanical method with which to do it, right? And later we'll see a proof of this if we have time, because I think it's simple and maybe many people have already seen it, but I think it does illustrate a lot of the examples. Yeah, absolutely. Resolution depth is equal to tree-like resolution depth. Yeah, there's no difference here. Yeah. So moving away just from XOR, it's not like all the lifting theorems that we prove are using the XOR gadget. A very popular gadget that people like to consider is this so-called indexing function, or also known as the addressing function. And the indexing function is pretty simple. So all it says is that, okay, if I have, if we think of the inputs as being partitioned into 2 groups, and we think of Y as being a big string and X as being a pointer into that string, and then we just output the bit that's pointed to by X and Y.
Robert, there was a question by Jan Johansson. I don't know if you could see the chat.
Yeah, I see
Yeah,
it.
he has
It asked if
already
resolution
answered.
depth was equal to tree-like resolution depth, and yeah, absolutely it is. Yeah, but you know, that's just because you can do the recursive expansion, but you know, the message of what I said is still true.
Robert, a quick question.
Yep.
So you mentioned when you replace the variables z with XOR gadgets, there is a blow up in the size of the formula in terms of W, right?
Yep.
But what if I performed a kind of a Sathan encoding so that the blow up is not there? There's only a polynomial blow up. So,
Yeah,
but the
then it would
results
trade off into the number of variables.
Ah, I see.
Yeah, that's true. You could do that, but then the trade-off would just go into the number of variables of the formula. So any lower bound that you proved would still be weaker in a corresponding way, right? You haven't somehow hidden the size, right? The size is still there. It's just encoded in a different parameter.
Right.
Any other questions? Okay. So back to this indexing function here. So we think of, in this indexing function, we think of like y as being a big long string, and then we think of x as just being a pointer into it. So all we do is we just take x, we consider it as a binary pointer, we point into y, and then we output whatever the bit that's pointed at by x here. And in some sense, the reason why the index gadget is nice and why we consider it all the time is because for many proof systems, which you can kind of think of as being query based, like they kind of, you can think of tree-like resolution, for example, you can think of it as DPLL, where we sort of query variables from the top down and we explore this proof tree in a sort of top down way. And this is also very, useful intuition for SAT solvers. And in some sense, this indexing function is a very difficult function for query algorithms to evaluate, right? The only way that we can really evaluate the indexing function by these top-down query algorithms is just you can't do anything better really than just evaluating all of x and then evaluating the corresponding bit of y. And a problem that comes when we wanted to find the composed formula with the indexing function here. So before with XOR, we were just sort of directly blasting XOR down into a CNF and substituting it in and then distributing. Well, with indexing, you're really going to get a giant, you really run into the possibility of getting a very big blow up when you do this, right? So usually when we encode the composed formula with index, what we do is we do a more sort of general encoding, which still turns out to be okay for all the proofs. So I'll just give a sketch of this encoding just so everybody gets an idea of what a more general idea of what these composed formulas can look like. So again, if f is on these n variables, z1 through zn, then this composed formula is going to look like this. So we'll introduce some xi variables and some yi variables, just like we did before. So the xi's are like the pointer inputs to the indexing and to the copies of the index function, and the yi's are the tables, like the truth tables that xi is pointing into. And the key thing here is that we've really encoded these pointers in unary. So for every single j in L, we're going to have a pointer variable that corresponds to that being the evaluation of the whole pointer input. So then now we can just sort of write down what this composed form is going to look like a bit more abstractly. So first we're going to say, okay, well, every single input has to have some pointer. The pointer has to point somewhere for every single input index. So we add these extra clauses that just say this. And then for every clause in my original formula of f, what I'm going to do is if I have zi in the clause, I'll substitute it with something that says, if the pointer from I to j is true, then output yij. This is just saying, if I'm pointing at j, then I should output, then that variable should really be yij. And if not zi is in the clause, well, then if I point to j, then I should really be outputting the negation of that bit. And then we just perform this substitution for every variable that appears in the clause and all possible choices of j that we can choose to substitute in. So this still gives you quite a blow up, but it wouldn't be as bad if you just directly blasted it down to CNF and then folded it out. At the end of the day, if your starting formula had width W and M clauses, then this composed formula is going to have something like, width 2W or L if these pointer clauses are the biggest one, and the blow up turns into something like L to the W, and that comes from this clause substitution where we have to plug in these xi's for every single entry there. Okay, cool. So what can you do with this indexing function? Well, the indexing function is intuitively much harder to evaluate than the XOR function is, and as a result, we can prove stronger lifting theorems for it. So a really nice example of this, which this follows the earlier template where the two proof systems P and Q are the same. If we let W of F be the maximum width of any clause that occurs in F, and we let W sub res of F be the minimum width of any resolution refutation of F, this is a pretty familiar parameter which controls size, complexity, and resolution. Well, then after composing with this index function, resolution size turns into pretty much exactly n to the resolution width. Okay, so here this is a kind of lifting theorem in the sense that now the proof systems are the same, but we've measured one complexity parameter of F, the width, and we've converted it into a size lower bound on F composed with the indexing function here. And it's helpful. It's kind of nice to contrast this with the other known results that connect width to size lower bounds, and such as the famous size width translation due to Bensasson and Victorson. Now, what's surprising about this is that the indexing gadget is not only hard for resolution. Once you compose with index, width doesn't lift to resolution size. It goes all the way to cutting plane size. So here's if people have seen the boot camp talks, they'll recognize this.
So Robert, can you go back one slide?
Yeah.
So for this result, the original formula that you started off with before you plugged in your gadget into it.
Yep.
What class of formulas is that? Is that randomly generated formulas, or is it a specific class of formulas, or what
this is any formula at all? This holds for any single formula.
Any formula. Okay.
Yeah.
Awesome.
Yeah. So it's very powerful in that sense. You have no constraints a priori on F. Of course,
by contrast,
the width of one comment is that if the resolution width equals the width of F in this case, well, then the size of the original formula is going to have size, n to the W already. So this is kind of not saying anything. But I mean, it's still tight, but it doesn't give you, it gives you the tight lower bound, but this gives you a much stronger lower bound on the resolution width of F. Thanks. Any other questions? Okay. Cool. So as I was just saying, resolution width, it turns out when you compose with this index gadget, it already lifts all the way to cutting plane size. So what's the cutting planes proof system? Well, maybe it'll be familiar if you've seen the boot camp talks. But the cutting planes proofs, in the cutting planes proofs, the lines are integer linear inequalities, and then we deduce new linear inequalities from them, kind of in the following way. So if I have two inequalities, then I can deduce their any non-negative linear combination of them. I mean, this is sound over real assignments. This doesn't really do anything for us for our purposes of considering proper proof systems, like 0-1 proof systems. And then we also have this division rule, which says, if I have some inequality AX and B, and I have some integer which divides all the entries of A, then I can divide by A on the left side, and then divide by D on the left-hand side, and then divide by D on the right-hand side while rounding up. And the reason for this is we're considering integer solutions for these X variables. So since A and B are integers, since everything here is integers, if I divide by D on the right-hand side, then this is already then I can happily take the ceiling just because I'm not dealing with real solutions. And the cutting planes proof system is a really nice proof system. It has lots of relations to optimization, and it's also been very sort of influential in proof complexity as one of these proof systems, which is kind of on the border for which I would say that we really understand. And one of the nice theorems that falls out of the previous paper that I mentioned that proved the thing for resolution as well is that lifting resolution width after composing with index already goes all the way to cutting plane size. So for any CNF formula at all, as long as I choose my indexing gadget to be sufficiently large, something like polynomial in n, like the number of underlying variables, then the cutting plane size of F composed with the indexing gadget is already n to the resolution width of F. So this is a real proper lifting theorem. It kind of relates two different complexity parameters of two different proof systems on different formulas. Okay. And I mean, this is just the tip of the iceberg. There's been a massive, there's been an explosion of these lifting results. Here, I've just listed some of them relating resolution in cutting planes. But you can see here that I can relate things like resolution depth to tree-like size, resolution depth to cutting planes depth, resolution width to size. And the gadgets, in general, they're not even restricted to just being XOR or the index gadget. So a very nice paper recently showed that resolution depth lifts to tree-like size, even if you plug in any gadget which has a very generic property, which we call low discrepancy. I don't want to get into the definition of it, but let's just say it's like a very, very nice property that many gadgets that you might consider, like inner product or lots of other functions, satisfy this. And then we have, I listed here just for the sake to show that, we can get lifting theorems outside of just this resolution and cutting planes. And that's if I start with like the Null-Stellensatz degree, like an algebraic proof system, we can compose with any gadget that has high enough rank and get a proper lifting theorem all the way up to cutting planes, modulo with bounded coefficients. Okay, so this is really kind of a powerful tool, and the applications are kind of growing by the day, I would say. Okay, and now it's not to say that these lifting theorems are just used to prove something like size lower bounds. They can also be used to prove trade-offs between lots of standard proof complexity parameters. So just for a sample, I mean, I don't have time to go into all the results here, but just for a sample of the kind of results you can prove, here's a canonical example for cutting planes. If I start with any unsatisfiable formula and I compose with the index gadget, well, then you can get a trade-off result between the line space in cutting planes and the size of cutting planes in terms of the resolution depth of refuting F. So I start with F. I have this, I take the resolution depth of F times this log n. This log n just comes up from evaluating the gadget. And we can actually prove a trade-off result. This says that neither space and log size can't both be simultaneously small. Okay? And I mean, even by taking this result and modifying it a little bit, there's other results by the same set of authors even, which shows how to get a three-way trade-off in cutting planes. So not only between space and size, but you can also include, say, space, log of size, and the maximum size of any coefficient in a cutting planes proof. So all three of these can't be simultaneously small, for example. Okay. So now, after you see all these results, you might be wondering, like, is there any rhyme or reason to them at all? Like, where is it coming from? Why is width correspond to size? Why does depth correspond to size? Why do these gadgets? What's the sort of underlying structure of everything here? And the answer is that it all builds on deep connections between three areas of complexity. So circuit complexity, communication complexity, and proof complexity. Okay. And in fact, when I was showing these strong proof systems earlier, the strongest possible way to state the results is to define these strong proof systems in terms of communication protocols. I don't really have time to go into the details of this, but this is just to let people know that there's some sort of systematic theory actually underlying all of this. So in the model of two-party communication complexity, in case you haven't seen it, we have two players, Alice and Bob. They want to compute some function together, but the input is bipartite. So Alice gets one half of the input, Bob gets the other half of the input. And then they want to output the function, and the only limitation is that they have to communicate bits with each other across this communication channel. And so their goal is to evaluate the function while minimizing the amount of bits communicated. And the message is that these protocols, in all the examples that I gave before, there is sort of a notion of communication protocol that actually the strong proof system corresponds to in this big table. And these protocols can simulate the proof systems, basically. So the relationship here is between refuting an unsatisfiable formula and solving the so-called unsatisfiable clause search problem. So given an assignment, given an assignment to my unsatisfiable CNF, find a falsified clause. Okay, so these protocols, they can simulate these earlier proof systems, and the lifting theorems actually lift these proof complexity parameters to these two communication protocol parameters. And it turns out that these communication protocols, when you define them this way, are equivalent to standard Boolean circuit models. So this basically generalizes this classical Karshmer-Wigderson connection from the 80s that connects communication complexity with circuit complexity. If you're not familiar with this, don't worry about it. This is just sort of an invitation in case you're curious. And I'll finally remark that we worked a little bit. We've worked on developing a more general theory that tries to capture as many of these lifting relationships as possible using subclasses of TFNP. So people who saw Christos's talk last week sort of saw these proof complexity. He sort of mentioned, the proof complexity has many proof systems, have natural interpretations as sort of query versions of these TFNP subclasses. Well, it turns out that you can also consider like communication complexity versions of these TFNP classes. And what these lifting theorems basically do is they relate the query complexity version with the communication complexity version. And that is the very general picture. But this isn't a complete picture. We've just managed to capture many of the things, many of the relationships that appear. And yeah, there's still lots of interesting work to be done in this direction. Also, let me comment that there's been recently, another thing you might point out is that why am I forcing myself to, evaluate independent, like put in independent new variables when I do this substitution? And there's been some recent work that's even been considering these kind of things, and you can still get interesting results in this case. So in a standard lifting, we have our formula F, and it's on some variables, and then we substitute in this G, and all of these G's are defined on totally independent input variables. And so you can naturally imagine coming up with some sort of generalized lifting where we allow overlapping on the input variables. So here I have the same number of X variables as I do Z's, but in fact, in the more recent theorems, you can even contract the number of variables here down even smaller. And if you wire these edges up, say like an expander or something like that, then it turns out that you can sometimes preserve the hardness of evaluating the composed function of F. The classic separation, if you're familiar with it, between regular resolution and resolution is basically of this type. We kind of compose with an index gadget, but we just use the same domain for all the possible copies of the index gadget. But recently, this idea has been sort of improved to give very, very strong trade-offs between things like tree-like resolution size and resolution width by Razborov. He showed that if I have a small width tree-like refutation, then if I go even a little bit below what the maximal width is, like if I have not the maximal width, if I go even a little bit below what a width for a small tree-like resolution refutation is, I can blow up the size of the proof even doubly exponentially. And there's also this nice recent work by Berkoltz and Nordstrom showing similar trade-offs on these overlapping gadgets between resolution width and resolution space. So how am I doing for time?
Well, if you want to take a few more minutes, that's okay, if it's few.
Yep. Okay, I'll just say a few words about this and then I'll finish then. So let me just say a few words about this sort of simple lifting theorem, just to finish off, just to give people sort of a flavor of how these things work. So the idea here, so here's the simple theorem we're going to use. We start off with any unsatisfiable formula you like. And what we'll argue is that the tree-like resolution size of F composed with XOR is at least 2 to the resolution depth of F. So now, everyone here is probably familiar with tree-like resolution. So we have a resolution refutation. It looks like this. We can resolve on individual variables, and of course we have this sort of top-down equivalent way of viewing this formula in terms of DPLL. So basically the idea is that if I replace each of these resolution steps with querying a variable from the top down, well, then I can explore down until I hit falsified clauses by my path, and then the overall size of the search strategy and the depth of the search strategy corresponds directly to the depth and the size of the corresponding tree-like resolution proof. So, okay, so how do we prove lower bounds on this depth, on resolution depth? Well, the idea is to use these prover adversary games, which are very closely related to the spoiler duplicator games that Joanna mentioned last time. And here what it is, well, we have this game, it alternates between a prover and an adversary, and this is just modeling a prover trying to generate a DPLL tree and an adversary forcing them to play as long as possible, right? So the prover selects a variable xi to query, and then the adversary selects some bit that forces the prover to go on for as long as possible. Now the prover's goal is to find a false clause in F, and the adversary's goal is to delay the prover for as long as he can. So say if we took this example, maybe the prover queried the variables according to this strategy here, and the adversary gets to choose, wants to force the prover to take a long path. Well, if the prover starts by querying x3, the adversary can force him to set it to 0. Then the prover queries x1, and then he forces it to 1, and then so on, right? Now we've got a 3-round protocol, a 3-round game here, and that's just because the depth of the corresponding proof here is 3. And there's a general connection that sort of characterizes resolution depth in this way. Sorry about that. Here we go. So in general, if you have an adversary strategy that forces all provers to take D rounds, then the resolution depth is at least D. And you can even characterize this in terms of upper bounds as well by prover strategies. So the nice thing about tree-like resolution is that there's also a nice way to use prover adversary games to lower bound tree-like size. So, I mean, here we have exactly the same game as before, but now the adversary, instead of always choosing bits, he can let the prover choose, and whenever he lets the prover choose, he scores a point. And when the prover chooses, he's always going to go to the smaller side of the proof without loss of generality. And so by mimicking the argument I gave a second ago, what you end up showing is that whenever there's an adversary that scores D points against the prover, well, then the tree-like resolution size of F is something like 2 to the D, okay? And in general, the idea for converting resolution depth to tree-like resolution size is pretty simple. If I start with a depth adversary over here on F, what I'll do is I'll just convert his strategy into a strategy for the adversary on the size game for F composed with XOR. And I won't go any more of the details because I'm already running a little bit over time, but the intuition should somehow be clear, right? Whenever the prover queries one of the bits in the 2 pairs of the XOR, the adversary lets them query it however they like. On the other hand, if the adversary queries, say, if the prover queries the second bit in a fixed XOR, then the adversary just looks at the depth adversary and sets it so that everything is consistent. And since the depth game adversary can push the game for D rounds, the size game adversary can score at least D points. So let me just skip over the proof here because I ran a little bit long. But let me just say here that the other lifting theorems in general use the same high-level strategy. So usually instead we use a prover strategy. So we'll say if I have a proof in the lifted space, then I can convert this back into an efficient proof in the unlifted space. So it doesn't always lift adversaries to adversaries. Sometimes it lifts proofs to proofs in the contrapositive direction. Okay, cool. So in conclusion, what I talked about today is just kind of the tip of the iceberg in these lifting theorems. And it's a relatively simple, but also very powerful tool to generate hard formulas and also get quite strong control over various proof complexity parameters. And I've just talked about resolution and cutting planes because there's lots of nice results proved there, but there's lots of other theorems proved for algebraic proof systems and semi-algebraic proof systems. And of course, also there's the whole realm of corresponding theorems of communication complexity and circuit complexity. And yeah, so the main message, I guess, is if you're interested in sort of getting some nice control over different parameters, this is a really powerful tool to have a look into. And yeah, thanks everybody for listening. So if anybody has any questions, go ahead.
Thank you so much, Robert. Questions, comments? Post it in the chat or just unmute and ask.
I have a question.
Yep.
So you mentioned that this lifting is something used in communication complexity. I was wondering, so this is in the model of 2 players. So would it also work in the, I mean, is there work of using lifting in the number in the forehead model?
Yes, yeah, absolutely. So in particular for Lovász-Schreiber proofs, there's been lifting theorems, like a few lifting theorems sort of relating the communication complexity in number and forehead to proving a very basically space length trade-offs, just like we saw for cutting planes for Lovász-Schreiber. I can give you some references if you'd like.
But does it reach size, or it has to be a trade-off?
Has to be bounded space. It doesn't go all the way up to size. And the reason is because when you're doing tree-like, like the number on forehead communication protocols are sort of inherently tree-like, and the Lovász-Schreiber proofs are, if you think of them as being DAG-like in general, well, then something kind of has to give in this tree-like to DAG-like.
Yeah, I keep forgetting that the communication complexity is a tree. Okay,
yeah, exactly. So there is DAG-like communication complexity, and you could conceivably define DAG-like number on forehead complexity, but I don't know if anybody's ever thought about that, to be honest. Yeah, it's a very nice question.
More questions, comments?
Well, Robert, would you be open to having like a tutorial on this at some point in the workshop?
Yeah, sure.
So yeah, we'll get back to you on that.
Depends on when, but yeah, of course.
Yeah, we'll chat later. Yeah, thank you.
Let me just comment, if I may.
Please.
Hello, hear me?
Yes.
Yes, I just want to say that there is no parity gadget in our paper with Russell. So we just had this game, but not this relation.
Right. Yeah. I was just saying it as a. I was trying to be careful in saying it's an easy corollary. I didn't mean to attribute it to you. Thanks, Pavel.
Okay. More questions, comments? If not, then thank you very, very much, Robert. And maybe let's take like 2 minutes to refill our coffee cup or whatever you're drinking, wherever you are. And we'll start in 2 minutes with Susanna's talk.